practical transformer such as a distribution transformer, it grows over time. As more and more houses are electrified, more the load of each house increases, so does the load on the transformer. So, it may very well happen that within the lifetime of a distribution transformer or any other transformer, a transformer that was designed to be sufficient for a given load, over a period of time the transformer may reach its rated load and the load may even exceed it. So, there are two methods by which such a situation can be handled. One is replace the transformer by a larger transformer. However, it has some practical limitations. For example, the larger transformer should be planned for future expansion, which means that the transformer rating should be relatively large compared to the present peak load. This also means, particularly for distribution transformer, that the new transformer will be operating at light load for most of the time, which is not a very efficient utilization of the transformer. The other approach is to connect a similarly rated transformer in parallel to the existing transformer. This has certain advantages. For example, even if the new transformer is of the same rating as the old transformer, then at least it allows for a growth of 100% in the load before a further replacement becomes necessary. Second thing, this new transformer need not always be connected. When the load is not sufficient, only one transformer may be connected and it can supply at its rated capacity. Maintenance also becomes easy because you need to keep only one spare small transformer. So, for these reasons, parallel operation of transformers are important, and in this lecture we will find out how to connect two single phase transformer in parallel, what are the conditions for that, and how to analyze parallel connected transformers. So, let us see. Suppose we have one single phase transformer connected to the load, to the source, on the primary side and supplies the load on the secondary side. This is, let us say, transformer 1. If I want to connect another transformer parallel to this, the primary of the two transformer will be connected in parallel to the source side. Also the secondary. However, while connecting the secondary in parallel, one should be careful about the instantaneous polarity of the voltages. For example, this is the instantaneous positive terminal of the parallel connected primaries and this is the instantaneous positive terminal of the secondary of the first transformer. Then the instantaneous positive terminal of the second transformer must be connected to the instantaneous positive terminal of the first transformer and the other terminal should be connected like this. If not, then one can easily understand if this polarity is reversed, then even without this load there will be a, once the switch S is closed, there will be a short circuit through the transformer winding and a very large current will flow. So, this should be protected against. So, before connecting the transformers in parallel, their instantaneous polarities should be checked and connected accordingly. This is the first condition for connecting two transformers in parallel. But this is not all. Obviously, one can appreciate that the no load voltages of the transformers should not be very different for the same reason, because even if we assume that there is no load and the transformer secondary no load voltages are different, then when we close the switch there will be a circulating current flowing through the secondaries, which will be limited only by the series impedance of the transformers, which we have shown to be, so we have seen they are small, within typically within 5 to 10%. So, even at no load a very large current can flow if the no load voltages of the two transformers are very different. So, the transformers to be connected in parallel should have instantaneous the correct polarity terminals connected together, and their no load voltages should be very close, if not exactly equal. There are few other conditions which are not essential, but desirable, and we will derive them. And of course, the total kVA rating of the two transformer must be greater than the total kVA demand of the load. It is for that purpose only that we are connecting the transformers in parallel. Now, let us see what other desirable conditions we can find out. For that, we will need to analyze this parallel connected transformer, and in the beginning we will assume that the transformers have identical no load primary and secondary voltages. The equivalent circuit of the first transformer with respect to the load side can be shown to be like this. We have derived this before. Let us say this series impedance is Z1 equal to R1 plus JX1. Since the secondary transformer, the second transformer input and output are connected the same source and the same load, effectively the series impedance of the second transformer will come in parallel to the first transformer. Therefore, the total equivalent circuit of the parallel connected transformers can be represented something like this. So, this is Z2 equal to R2 plus JX2. Let us say the total current drawn by the first transformer is I1, the current drawn by the second transformer is I2, and the total load current is IL. Then one can easily derive that Z1 I1 equal to Z2 I2 and IL equal to I1 plus I2. Therefore, in terms of IL, I1 equal to in terms of IL, I1 equal to Z2 divided by Z1 plus Z2 into IL, and I2 equal to Z1 divided by Z1 plus Z2 IL. Now, let us try to see the phasor relationship between these currents and voltages. Let us say this is the load voltage phasor VL and this is the load current phasor IL. The vector sum of phasor sum of I1 and I2 is equal to IL. So, let us say this is I1 and this is I2. Then from this equivalent circuit we can show this is V1 dash. Similarly, this is equal to I1 Z1 equal to I2 Z2. This is how the phasor diagram will look like. Now, it is obvious from the phasor diagram that the current in the two transformers will be minimum when I1 and I2 are in same phase, because then IL will be the algebraic sum of I1 and I2. Therefore, one thing we can immediately say that one desirable condition for parallel connected transformer is that when they are connected in parallel, the currents drawn by them are in phase. That will happen only if I1 and I2 are to be in parallel, then I1 by I2 is equal to Z2 by Z1. Therefore, if I1 and I2 have to be in phase, then the ratio of I1 by I2 will be a scalar, and that will happen only if angle of Z2 is equal to angle of Z1. That is, the ratio of R1 by X1 is equal to R2 by X2. So, this is a desirable condition, although not essential. This will ensure that for a given transformer current rating, the maximum load current can be supplied. From the previous circuit diagram, we have seen I1 equal to Z2 by Z1 plus Z2 into IL, and I2 bar equal to Z1 divided by Z1 plus Z2 IL. Now, multiplying both sides of this equation with VL star, we get where star denotes complex conjugate equal to Z2 divided by Z1 plus Z2 into IL VL star. Now, VL star I1 is the KVA complex KVA supplied by transformer 1, while VL star IL is the complex KVA demanded by the load. Therefore, we can write S1 equal to Z2 divided by Z1 plus Z2 into SL. Similarly, S2 equal to Z1 divided by Z1 plus Z2 into SL, or S1 bar by S2 bar equal to Z2 by Z1 hence, if we look at the magnitude alone, S1 by S2 equal to mod Z2 divided by mod Z1. Now, it is desirable that under any given load, under any given total load, the transformers share the load in proportion to their individual KVA rating, which means for any given load we would want S1 divided by S1 rated should be equal to S2 divided by S2 rated. Therefore, this translates to S1 divided by S2 equal to S1 rated divided by S2 rated, that is the transformers shared the KVA total load KVA in proportion to their individual KVA rating, but this we have seen to be equal to mod Z2 divided by mod Z1. Hence, for sharing the load in proportion to their KVA, we find that the series impedance of the transformer, the magnitude of the series impedance of the transformers should be inversely proportional to their KVA rating, that is Z mod Z should be inversely proportional to S rated. So, that is another desirable condition for connecting transformers in parallel, that is the series impedance of the transformer should be inversely proportional to their KVA rating. This can be stated even in a simpler form if we note that the original relation is S1 rated divided by S2 rated equal to mod Z2 rated mod Z2 divided by mod Z1, or S1 rated can be written as VL I1 rated divided by VL I2 rated equal to mod Z2 divided by mod Z1. Or we can write I2 rated into mod Z2 divided by VL equal to I1 rated mod Z1 by VL. Now, if both the transformer has a rated secondary voltage of VL, then this is Z2 per unit PU is equal to Z1 PU. Therefore, in simple terms, the parallel connected transformer should have equal per unit series impedance on their own base. That will ensure that the transformers will share the total load kVA in proportion to their individual kVA rating. Now, suppose this condition is not satisfied, that is, let us say S1 rated divided by S2 rated is greater than mod Z2 by mod Z1. Then what will happen? This thing can be written as into mod Z1 by mod Z2 larger than 1, or S1 rated by S2 rated into Z1 is greater than Z2. In which case it can be easily shown that it is the second transformer which will share more load and reach its rated kVA earlier, because we have seen S2 to be Z1 divided by Z1 plus Z2 into SL. Now, let us say under certain load condition S2 has reached its rated kVA S2 rated. Therefore, S2 rated equal to mod Z1 divided by mod Z1 plus Z2 into mod SL, let us say SL max. SL max is the load kVA that is reached when S2 reaches its rated kVA. In other words, SL max is equal to mod Z1 plus mod plus Z2 divided by mod Z1 into S2 rated. So, what is the load on the first transformer then? S1. S1 is given by S1 equal to mod Z2 divided by mod Z1 plus Z2 into SL, and when S2 reaches is rated kVA, then the load kVA is SL max. So, this should be SL max. So, this can be written as, substituting SL max from the previous equation, we get this to be mod Z2 divided by mod Z1 into S2 rated. But we have seen mod Z2, from this relation we have seen mod Z2 by mod Z1 is less than S1 rated divided by S2 rated. Therefore, S1 equal to mod Z2 by mod Z1 S2 rated will be less than S1 rated divided by S2 rated into S2 rated, or the conclusion is S1 in that case will be less than S1 rated. Therefore, we see that if this relation is not satisfied, then one of the transformer with the lower series impedance reaches its KVA limit first, and beyond which it will not be possible to load the parallel combination. Therefore, the other transformer will still have some capacity left. Therefore, in such a situation we will not be able to utilize the total KVA capacity of the two transformers. So, it is desirable that the per unit impedance of the transformers be same on their own base. The impedance angle of the two transformers also be same, so that the total KVA can be maximized. Now, this was the analysis of parallel connected transformer, assuming the two transformers have identical no load voltage, but in practical situation this is not always possible. There will be a small difference between the no load voltages of the two transformer, in which case the question arises, how do we analyze parallel connected transformers. Again, this is the first transformer. The second transformer again is connected parallel to it with appropriate polarity. Now, these two transformer primaries are connected to the same source, but their induced voltages are slightly different. That is because their turns ratios are not exactly same. So, if we want to draw a equivalent circuit of this situation, then we must recognize that now this impedance will not exactly be connected in parallel, but for the first transformer we can still draw the equivalent circuit with respect to the load side. So, this will be V11 dash, that is with respect to the secondary of the first transformer. This is the impedance of the first transformer, series impedance of the first transformer, and this is the load impedance. Similarly, we can draw the equivalent circuit of the second transformer. Now, since the turns ratio is different, the applied source referred to the secondary side of the second transformer will not be V11 dash, but it will be some other voltage V12 dash, but they will be connected on the load side. Again, let us say this current is I1, this current is I2, and this is the total load current IL. So, this will be the equivalent circuit of the parallel connected transformer when their no load voltages are not identical. The problem is to find out the individual currents I1 and I2 contributed by the transformer when the total load current is IL. In order to achieve that, we can write the node voltage equation at this point, assuming this voltage to be VL. We can write VL divided by ZL equal to VL divided by ZL equal to V11 dash minus VL by Z1 plus V12 dash minus VL by Z2, or VL YL equal to V11 dash Y1 plus V12 dash Y2 minus VL Y1 plus Y2, where YL equal to 1 by ZL, Y1 equal to 1 by Z1 and Y2 equal to 1 by Z2. Hence, we can write VL into YL plus Y1 plus Y2 equal to V11 dash Y1 plus V12 dash Y2, or VL equal to V11 dash Y1 divided by YL plus Y1 plus Y2 plus Y2 divided by YL plus Y1 plus Y2 V12 dash. Therefore, the current I1 equal to V11 dash minus VL Y1, this will be given by Y1 into or I 1 equal to y 1 into y 1 plus y L plus y 2 into V 1 1 dash divided by minus y 2 V 1 2 dash divided by y L plus y 1 plus y 2. Or I 1 equal to y L y 1 V 1 1 dash plus y 1 y 2 V 1 1 dash minus y 1 divided by y L plus y 1 plus y 2. The value of I 2 can be found in a similar manner, and once y 1 I 1 and I 2 are found out, the KVS applied by them can also be determined. Now, let us look at a problem. Let us say there are two single phase transformers with voltage rating, open circuit voltage both of them, that is they have identical no load voltage 11,000 volts by 3.3 kV. Now, on short circuit test with the HV winding shorted, the first transformer one gave the following data. The applied voltage is 200 volts, the circulating current is 400 ampere, and the dissipated power is 15 kilowatt. For the transformer 2, again with the HV winding shorted, the test data is applied voltage 100 volt, circulating current 400 ampere, and power consumed is 20 kilowatt. Now, these two transformers are connected in parallel and they supply a load current of IL of 750 ampere at a 0.8 pf lagging power factor. We are to find out the KVA supplied by each of these transformer and the load voltage. In order to do this, let us first find out the series impedance of the transformers. So, for transformer 1, mod Z1 equal to 200 volts by 400 ampere equal to 0.5 ohm.
and R1 equal to 15 into 10 to the power 3 divided by 16 into 10 to the power 4 ohm, that is equal to 0.094 ohm. For transformer 2, for transformer 2 mod Z2 equal to 100 volts by 400 ampere equal to 0.25 ohm, and R2 equal to 20 into 10 to the power 3 divided by 16 into 10 to the power 4 equal to 0.125 ohm. Now, x1 equal to square root z1 square minus r1 square equal to 0.491 ohm, x2 equal to square root z2 square minus r2 square equal to 0.2165 ohm. Therefore, we can write the angle theta 1 equal to cos inverse r1 by z1, this comes to 79.1 degree, and theta 2 equal to cos inverse 0.r2 divided by z2, this comes to 60 degrees. So, z1 equal to 0.5 ohm, angle 79.1 degrees, and z2 equal to 0.25 ohm, angle 60 degrees. Please note that here the impedances do not have the same angle. Nevertheless, we can still proceed in a similar manner. So, what is Z1 plus Z2? This comes to 0.7407 ohm, angle 72.8 degrees. So, what will be the current I1? I1 we have seen to be equal to Z2 divided by Z1 plus Z2 into IL, that is equal to 750 amperes, 0.8 lagging power factor, that corresponds to minus 36.8 degree into 25 angle 60 degrees divided by 0.7407 angle 72.8 degrees. This gives you the current I1 2. So, I1 equal to 253 amperes, angle minus 49.6 degrees. Similarly, I2 equal to Z1 divided by Z1 plus Z2 IL equal to 750 angle minus 36.8 degrees into Z1 is 0.5 angle 79.1 1 degrees divided by 0.7407 angle 72.8 degrees. This gives you I2 equal to 506 amperes angle minus 30.5 degree. Please note that the algebraic these two currents are not in phase. Therefore, their phasor sum instead of being 759 ampere, it is just 750 ampere. So, that is what happens, that if the angles of the series impedance are not same, the total current that you can supply reduces. Next, let us try to find out what will be the load voltage. For that, let us try to draw the phasor diagram. So, let us say this is the load voltage VL, I1 is at a larger lagging angle of 49.6 degrees, but has smaller magnitude. I2 has a larger magnitude, but a smaller angle. This is I1, this is I2, and this is the total current IL. So, the impedance drops are like this, and this is the applied voltage V1 dash. Let this angle be delta. Now, we know V1 dash magnitude is 3.3 kV, because the applied voltage is 11 kV. Now, V1 dash here equal to 3300 volts at an angle of delta. VL equal to magnitude of the load voltage at an angle at 0, that is, we have assumed this to be the reference phasor. I1 equal to 253 amperes angle minus 49.6 degrees, I2 equal to 506 amperes angle minus 30.5 degrees, and IL, their phasor sum, equal to 750 amperes angle minus 36.8 degrees, and this phasor is equal to I1 Z1 equal to I2 Z2. Now, if this angle is phi 1 and this angle is phi 2, then we can write V1 dash equal to VL plus Z1 I1 equal to VL plus Z2 I2. Now, this angle is the impedance angle of Z1, that is, this is theta 1, and this angle is the impedance angle of Z2, that is theta 2. And this angle is phi 1, this angle is phi 2. So, theta 1 minus phi 1 equal to 5 degrees, and theta 2 minus phi 2 that is also equal to 29.5 degrees. So, we can write from this phasor diagram 3300 cos delta plus minus 126.5, which is 0.5 into this 0.5 into I1 Z1 I1 cosine of 29.5 degrees, that will give you VL. Also 3300 sin delta equal to 62.3, from which we will find out VL to be equal to 3190 volt. The KVA supplied by transformer 1 will be VL I1, this comes to 807.5 kVA at a lagging power factor of 0.648 lagging power factor, and S2 equal to VL I2, this comes to 1615 kVA at 0.862 lagging power factor. Thank you.